Hey everybody, how you doing? Hopefully everybody's okay. We're going to start out by just kind of reviewing in a graphical method here of direct variation leading into slopes and lines and linear functions. So what we do is we have to remember a couple of things about our notation. And a point is just some place where you are. And it's given by a horizontal and a vertical distance, if you will. Okay. Um, and what we're doing here is we're just seeing if we can fit patterns together and how things change. So we start at the origin, which says that we are moving 0 in units in the horizontal, the x, and we're moving 0 in the vertical y. So where we are is where we are. Now, what I'm going to do is I'm going to pull up a couple things here, so don't be too worried about it. But let's say we want to move forward 1 unit. And we know that that point now is 1 unit positively 1 unit and 0 unit on the vertical. So another way of saying it is I've only gone in one dimension. I've only gone 1 unit in one dimension, and I'm moving forward positively in that unit. So my run, it will be 1 unit. Now, when we look, if we want to talk about the verticals here and how they change, well, let's say we go up 1 unit, and we have a point, we know it's 1 comma 1 now, because we've gone 1 unit in the positive horizontal direction, and now we've moved 1 unit positively in the vertical unit, okay, or the vertical units. So we all know that 2 points define a line. So I'm going to bring that up, okay? So here's our line that we're looking at. It's kind of nice, right? It's not bad. Notice that I have it dotted. I'm dotting it here to show you that there are infinite number of points on this pattern, this line, this linear function. And the slope will be 1. It will be a constant rate of change. In this case, because it's direct variation, the constant rate of proportion or proportionality is the same as the slope. So we threw in some new notations, right? And one of the biggest ones was this whole delta thing, right? So what we're saying here is that remember a point itself, some point x comma y only means this, that we're changing someplace in the horizontal and vertical positions. Now, when we look at that, we can also say that's our input values and our output values. Now, when we later talk about this, we'll get into other notation called functional notation. But for right now, this is good. So, what did we actually do? We changed. We had a difference of things to get to the place that we needed to get. So, what we have here is, remember, we introduced delta, right? And delta is a difference. And that's the easiest way to put it. This is delta. And notice that they both start with the same letter, D. D, delta. Delta, difference. So we're taking a difference of two things. So let's look a little closer at this horizontal change right here, okay? So what we have is a delta horizontal or a horizontal change, a difference in the inputs. So we have two different inputs. We have 0 and 1. Whichever one you pick, you have to keep the same pattern. So I'm going to call this x sub 2 right now, and I'm going to call this x sub 1. Whoops, I wrote 2, but it should have been 1. So this is actually the difference between two inputs, or horizontal values, which simply means that in the x sub 2 category, we have 1, and in the x sub 1 category of the original point, the origin, we're lopping off 0, which just means that we've moved 1 unit positively. Now, I'm going to delete a couple things here real quick, just to clarify. And now what I'm going to do is I'm going to look at this change in heights right here, okay? So that's what I'm going to be looking at. Now, I'm going to call it delta y. And now I'm just looking for a difference between two different y values. So I'm going to call this point the second point. So I'll call this like point 2. And I'll call this one down here point 1. So now we only look at the y values, the vertical values, the outputs. And that is clearly in the second one, 1, and in the first one, it's 0. So it's 1. Now, if we put our old names together, this would be our rise or vertical change, and that's a better way to say it, vertical change. And our run, which is our horizontal change. Okay? So when we put those two together and make a proportion, when we make this kind of beautiful pattern called slope, we denote it using the letter M, and you'll see why in a moment, hopefully, but M is simply delta y, or the rise, over delta x, or the run. So I'll write that down. Rise over run, like that. So we have a proportion. We're consistently, constantly going in this kind of movement. Oh, well, I wonder. M, move. Oh, so slope might be the way that we move. That might be a reason why we could remember M as slope and M is move, and move is M, which is slope, which is rise over run, which is delta Y over delta X. There's lots of little names for it. But if we put it all together now, right? If I put it all together and just put it into a little statement, I could say slope is the change or the difference in the verticals divided by the change or the difference in the x's. And since we already did the calculations above, we know it's 1 over 1, which means that I'm moving 1 unit in the positive direction on the y, and I'm moving 1 positive direction on the x. So horizontal and vertical. So that means the slope is 1, and we can just simply write slope is 1. Now, I'm making a bigger box here for a second because you remember in direct variations, we always go through the origin. So in this case, it's also k. And that means a lot to us, okay? Now, with all of that being said, and it may look a little bad at first, let's see if it really is as bad as we're making it out. Okay, so I'm going to delete a few things here to make some more room. And what we're now going to look at is another point that is on the line. Now, any kind of point that is on the line is what we call a solution to the equation or model that we're developing. So, everybody okay? All right, hopefully. Okay, here we go. So, I've gotten rid of a few things here. Now, what happens if we go over 4 units now in the positive direction? So I'm going to have to zoom out a bit here. I've moved over now 4 units in the positive horizontal direction. I'm now going to make a point. We know that that point, we know that that point is 4, 0. We've moved over 4 units in the horizontal direction, in the positive horizontal direction to the right, okay? Now, let's say we want to make sure that we're on the same line, right? Well, we can count how many times we're going to go up because we're not going to be going down, right? Because the line clearly looks like it's moving up, if you will. As the x's increase, as the inputs increase, the outputs are also increasing. This is also known as a one-to-one because you'll notice when I go up 4 units, we are now at a point 4, 4. Notice the solutions that are on the line, 1, 1 and 4, 4. It's one-to-one. So whatever input we get is the output we get. So our constant rate of proportionality in this case would be 1. Okay, now let's take this a little bit further, and I'm going to go into another little tiny piece here. I'm going to get rid of the rises and the runs, and hopefully show you a bit more about some other interesting components. So here's our line. And at this point, what I can do is I can make this solid so we have a better grasp that it is a line that represents infinite solutions. At this point, what I'm going to do is remind you of our equations here for direct variation. Now remember, for direct variation, we had what? We had our y equaling kx. So the k was a constant of proportionality. If we solved for k, all that means is we're dividing both sides by x, so that says that k is y over x. Oh, that is remarkably similar to m, which we said was delta y over delta x. Now, when we look at this and we have some fun, okay? Let's say that the slope in this case is going to change. So let's get rid of this whole menu thing here and let's play around with it. Let's say I have a slope of 0. What do you notice? If I keep rotating, oops, maybe I shouldn't have used that word, but do you start to see some really interesting patterns around? You guys okay? So the slope is really showing us a direction, how to move. Like if we're starting at 0, 0, and I want to move a little bit over here to the, to the left, if you want to look at it that way, or up, then I can tell myself I can turn this way or this angle and move. Wonderful proportionality. It's not going to change. You okay? Should be asking a couple. I hope you do. That's when a slope is 1. Notice that the points 1, 1, 4, 4 still exist. Well, let's go all the way up to 3 here. Now look at it. That looks really nice, right? But you'll notice in the horizontal, we've only moved over 1 unit positively, but how many units have we moved up vertically? 3. Point 0.5, right? 0.5 and 1.5. Then there's 1, 3. How about 4? Can we go up to 5 actually? Notice we've gone over 1 unit in the positive direction, and we've gone up 5, and there is a point that crosses, right? That's where our point is. So the point here being is that direct variation is a nice way to get into, well, the slope equations and things like that. Now, let me go back to a slope of 1. Let's keep this kind of normalized, okay? So the rise equals the run in this case, right? Now, I want to show you something else. What does this b mean? Well, if I go back to my function here, and I wrote it in a basic way, y equals mx plus b. So, if you note on a direct variation, the b is 0, right? So that means that all we're dealing with is y equals mx. Well, I don't know about you, but that looks very similar to the direct variation equation. So, what would happen if we add something to our what? Well, it says y. You see it right there in purple? I'm clicking it on and off. It says y. That's output. So, if I take mx, which is some product, some output, and I add or subtract it, then all of those solutions should be either vertically changed up or down. Well, let's see what happens. Let me zoom out just a bit here. Give myself a little more room. How about right there? Maybe that's good. Okay. Now notice the B. Okay, I'm going to use a slider, and I want you to tell me what happens as I move it to the right. Are the numbers increasing as I go from 0 to 0.5 to 2 to 2.5 and to 3 and to 3.5 and to the mysterious 4? Notice the pattern. Notice what's changing. Just the vertical components here, right? The whole line is staying the same. It's not doing that movement thing, right? It's not changing the direction. It's just changing how we start. Or maybe there's another word that might be pretty interesting to use. Oh, and wait, if we go in the negative, we're all falling. You guys okay? Notice how the outputs change. We're changing ups and downs. And by doing so, having a little bit of fun, changing a couple of other aspects. And I hope you see it. Okay. Now we can get into more discussion in a lecture setting. But when I pull this all together now, and if I use my pen And I simply say, well, what we were doing, oh, I'm going to have to keep that up, aren't I? Yep. I wish we could have kept that at the same time, but that's all right. Um, all right, so when we pull all this together, our direct variation equation, right, that we came up with was simply y equals kx, which then tells us k is y over x. We now know that there's another one, y equals mx, and we can also just simply say that in this case, k is equal to m. Whoops, I've got to move that. Okay. Now, we are saying that this is an output and this is a product of some constant of proportionality and an input. But together, they make an output. So if we extrapolate some of this information, we can see that we can say y equals mx plus b. Under direct variation, b would be 0. And remember what I said about m. M is slope, but m could also be how we would do what? I just hit the button, ironically. Move. So if I put this all together just very quickly, this is maybe how we move, and this may be where we begin. Those might be nice ways to help remind us about how things work. So I'm hoping you now have a concrete or a much more concrete understanding in both the geometric and the algebraics of how we're looking at building linear functions. And soon enough, we're just about at the turning point to stop using y, because as you can see, y can get very confusing after a while. Besides, who wants to always ask why? Why? It's kind of fun. But anyway, I hope this helps a little bit, and I hope you had some fun doing it. And we'll get into actual calculations with this, okay? But you'll be able to see how things change, and that's one of the objects of this course, is to see patterns and how relative patterns can change. Hope everybody's okay. Have a great day. Bye.